here we go. So as one example, we've been doing these density models fitted to, and I kind of wish I'd put in the plot showing the location of data for this species, but walleye pollock, total global catch of fin fishes is somewhere around 90 million metric tons, of which 1 to 2 million is walleye pollock. So over 1 to 2% of global catch is walleye pollock. It's the largest volume of catch in the U.S. It's processed at sea to generate fish sticks and fish sandwiches and so on and so forth. And we always consider the stock to be this sort of Eastern Bering Sea, but recently it's colonized the Northern Bering Sea, and this sort of 1,000-kilometer northward movement, invasion of an ecosystem that used to be ice covered prior to climate change. So in this case, this is showing a reconstruction of density across the Eastern and Northern Bering Sea. And, when people ask me about sort of rapid and ongoing climate change, I find it pretty intuitive to point out that in 2010 or 2011, say 10 years ago, Norton Sound had no pollock. St. Lawrence Island here, where my mouse is, was basically surrounded by areas with almost no pollock, shown in this color, kind of bad color scale in green. And then we believe that starting around 2014, after as ocean warming, as we went into a warm stanza, that pollock started moving northward until by 2017, 18, and 19, there's a hot spot of density right up against the Bering Strait. This line here is the convention line between the US and Russia, and a lot of pollock, we believe, have moved into the Western Bering Sea. We have fishing boats that have been out, and then Russia has done unexpected military training exercises. So that sort of kind of international incident is sort of on the rise, both here and other places. And there's a bunch of sort of like little very small shooting wars that have broken out over fish stocks over time that are thought to become more likely as fish shift their distribution in response to climate change. So, the model is essentially going to predict densities across a landscape. In this case, it's a single variable for a univariate model. We could do this for a multivariate model. And once you have those densities across a landscape, you can predict these sort of derived quantities, so that the northward center of gravity, like the mean location measured as kilometers north of the equator, has moved, looks like this, with a standard error that propagates uncertainty and represents, a nearly, in this case, I'm trying to read the plot. I mean, about a 200-kilometer northward movement from 2012 to 2019. The northward range extent is much even greater than that, but the center of gravity moving 200 kilometers north is also a huge change. And then the effective area occupied is also increased over time. So the population has the lowest effective area occupied. This is in log square kilometers, so a hard to think about unit, but it was lowest around 2010 and has since gone up hugely outside the historical range by 2015. So these are sort of consequences of, these are types of inference that you can make once you can predict density across a landscape. And obviously these are types of statistics that we care about for kind of climate, climate analysis. So, those are just a few kind of examples. Here's sort of a full list. So, once you have density across a landscape, you can get a measure of total abundance. Measuring population trends, like that's an input that you could, we do put into stock assessments as a data input, so if somebody's trying to make a new stock assessment for, a lake, based on seines and weirs and angling effort. Somebody could make a model of that using gear as a catchability covariate, and then take the outputted estimate of total abundance and use that as an index of abundance. And that's essentially what we do for many of our, some of our stock assessment models in Alaska now. You can also get a measure of average density. So that's a per capita measure of how many, what's the average, on average across individuals, what's the average density in their environment, in their vicinity. And that might be a better measurement of density dependence than just total abundance, because density dependence we think occurs locally. Things probably are locally depleting prey or exceeding their access to physical refuge from predation, not just based on every population in the world, but based on how many are near them. So a spatial measure of average density might work well. You can look at distribution shifts, range expansion or contraction. That's sort of a metric that the IUCN Red List uses, but we don't use in fisheries too often. You can look at sub-area abundance. You can look at availability to different ports. You can look at overlap in multivariate models. You could look at overlap between predators and prey as a measure of predation, likely predation pressure. You can look at both kind of local covariates and regional covariates. You can forecast. You can look at correlations across species, both to defined complexes or assemblages and so on. And then there's, even more kind of derived, there's these set of kind of multivariate models that fit numerical density or biomass density, as well as a measure of condition or size or stomach contents, and, or bioenergetic calculations. And so all of these are ways of making kind of landscape scale inference. Is this place is there better, is the energy density of prey exceeding metabolic requirements more in this place than this place? How is that changing over time? These are all types of kind of ecological inference that hopefully people can see how might be useful in their work, but it's not typically been something that we calculate, and use for statistical analysis. I'll just point out that there's been a bunch of papers, many of which I've been involved with, but not all of them, that do sort of simulation testing. So, most recently we used a simulator for, I think, for skipjack tuna. I'm going to forget offhand, using this software called CPDEM, and then simulating different sort of spatial footprints for a fishery and seeing how well fishery CPUE works as an index of, to generate an index of abundance. So, the point is that you can use these types of models as an operating model to explore how much your data is degraded by changes in gear or changes in the spatial footprint of sampling. I'll try to get through a few more slides before switching to code. So, my kind of, take it with a grain of salt, but, my feeling about the benefits are that you can combine multiple data streams. It's a disciplined approach to propagate uncertainty about spatial sampling designs. It can improve your precision by accounting for the portion of variance in your data associated with randomized sampling location. And, it can improve communication, ecological inference, and intuition by doing these sort of bringing in concepts of spatial concepts for your inference. The drawbacks, of course, are that the results are model-based and so affected by user decisions, in which case you need to communicate that and come up with some kind of standards if it's used operationally. There's a potential to introduce bias, which simulations suggest is likely to be small, but it's worth noting. Presumably nobody will come out of this thinking that any of this is simple. I do think that the software interface is increasingly straightforward. And I think that the concepts in terms of that linear predictor, for anybody who's sort of familiar with a glim or a gam, it should make sense intuitively at some, after some amount of use and exposure. But it's sort of irreducibly complicated to think about multiple species across space and time. And then there's just many decisions to make. And so people can end up spending a lot of time doing it. And that's a drawback when that focus on software or statistics detracts or takes time away from actual, thinking about ecology or what makes sense. So there's benefits and drawbacks. And then there's kind of a set of diagnostics. So I wish I'd updated this plot. These tests are based on software called Dharma that we started using, and those tests, we have simulation studies showing they don't mean anything. But you can get these sort of model predictions against residual plots. So this is sort of a standard model diagnostic, or you can compute it as a QQ plot, which is kind of what's shown on the left here. You can also aggregate those and compute them as Pearson residuals or as quantile residuals across a landscape. So there's sort of a standard set of diagnostics. And yeah, great. I'm sharing my screen. I got nervous there that so just to switch over to the kind of code portion of this. The main thing for me, I mean, the way I'm doing this is everybody can do, project management on their own machine, however they choose to. Kind of like a cooking show. I've got kind of a model that I already ran, and I'll start a new model just so people can see me do it for whatever that's worth. So I'll make a new folder called example 1 index on the fly, and I'll just then I'll set that as my working directory. And anyone feel free to jump in with questions here too if you choose to. Of course. So the point is that VAST has a sort of a terminal, generates terminal output, kind of like a standard package in R, but it also generates, writes a bunch of stuff to file, kind of like the R4SS output of StuxSys or StuxSys itself that runs as an executable. And so, for operational code, it's nice to have sort of a permanent record of what you ran. So I'm hoping that I typed that in right, but and then I'm just going to go to this index standardization. It's the top example here, and I'm just going to start it running, but using, replacing this set working directory line with where I want it to go. I'll just get this running. So it has this terminal output where, I mean, it's about as fun as watching, somebody mow grass. But, it's saying that it's writing output to a directory. It's making the extrapolation grid. So by default, the region equals whatever I put in example region, which we can see in a second. And then it's reducing that down to a certain resolution that's also specified in make settings. Actually, maybe I'll do this more slowly. I'm sorry. Instead of running it as a batch, I'll just kind of do what makes sense, which is just actually show what's here. So the data that was loaded includes example region. Sampling data is this long form data frame. So it's just a list of catch in kilograms, the year, the area swept, the latitude and longitude, and then some other kind of legacy nonsense variables that you can ignore. The region, is specified as Eastern Bering Sea, which VAST internally looks up a shapefile. But if people have other data sets, they can define it in other ways that are listed on the wiki. And then I've got a bunch of covariate data in the example too. So I forgot. I've got it loaded into the package. I've got this the spatial extent of the cold pool. in square kilometers. And so you can kind of see that cold pool, this sort of area of cold water in the Bering Sea, went from 20,000 square kilometers down to about 6,000. No, 200,000 square kilometers. Yeah, down to about 6,000 recently. So that's sort of the signature of declining sea ice in the Bering Sea. But that's the type of covariate data that a person might be able to put in. The next line after loading that example data set was this make settings function. So make settings is one of these three kind of workhorse functions. And people are free to look at the details here. It generated sort of this list of settings by default, like the version of the CPP, 100 knots in the Eastern Bering Sea. Field config is sort of a critical decision about sort of the spatial and spatiotemporal stuff that I will not get into yet, and some other decisions. So let's see, where was I? So in this case, I'll start it running again. And you can, again, just kind of see the terminal output. And I'll switch over to where I ran it before this morning. Let's see. So this is where I ran it. I ran the exact same code earlier. And so you can see up here where it produces some of the same output. It says making extrapolation grid. That's what we're seeing right now. And then it makes spatial information. Now it takes a little time. It reiterates what some of the decisions were. It lists out the number of parameters being estimated. So in this case, there's about 100 fixed effects and about 10,000 random effects. And then it has this sort of table of parameter estimates until it finishes optimizing the the negative log likelihood gets down to a low value and sort of stops moving when it gets close to MLE. And then I ran this plot function on the output. Plot is the plot results function on the S3 class that it recognizes as the output of fit model. And it generates a bunch of plots that I'll just switch over to here. So the model is I'll skip NISO for the moment. Here is sort of the summary of location. So, and these could be better labeled in the future. But by default, it's measuring the kilometers north of the equator of just the Eastern Bering Sea. So this won't look exactly the same as the PowerPoint where we were fitting the Eastern and Northern Bering Sea data at the same time. But you can see this sort of steady movement northward, even in the Eastern Bering Sea, about 100 kilometers northward over 30 years. And I guess this is Eastings, which is getting smaller. So it's moving west a little bit over time with these big cycles as cohorts move through in one or the other area. Here's the extrapolation grid that it's producing in that other terminal and the location of these knots that it's using. Here's the location of data. I won't get into the effective area occupied in square kilometers. So different from the plot I showed before now in natural space. And so you can see that it went from on average occupying about 150,000 square kilometers to now being almost 250,000. So it's almost doubled in the sort of effective size of the population as the cold pool is shrunk. An index of abundance shows that it got to its lowest level during, let's see, I guess that was during there was sort of a warm stanza in the early 2000s that led to lower recruitment. And so even though this was cold conditions when they typically do well for recruitment, they had a bunch of bad cohorts coming through. The index has since gone up to a very high level, and then that's going down again a little bit. These are the viridis color scale plots instead of the kind of shitty rainbow color scale I used to use. And this should look similar where like in the in years with a large cold pool, they stopped inhabiting the northern portion of the Eastern Bering Sea, and they've since colonized that. Here's the same kind of residual plot, or quantile residuals on a map. And so it's worth looking at these just to confirm that there's no big spatial pattern in residuals. There's definitely little bits of spatial pattern that occur in the northern Bering Sea, where there's kind of complicated dynamics occurring. But I look at these and I don't see a huge, I mean, when people do breakout groups, they'll see more tightly configured models generating more obvious spatial patterns and residuals. Here's the northward. Let's see, that's the eastings and northings. So this is the northward range edge. So 95% of the biomass, the population is south of this northern range edge, which is in the Eastern Bering Sea, not showing anything super interesting. Yeah, so those are some of the standard outputs. And, you know, there's also this sort of record of the package that was used. There's a record of the parameter estimates, which it's worth looking at. Actually, I should walk through this. So this is also what is generated and available as terminal output. So the RPAC, where I ran fit model, I can get that same parameter estimates output. So like this is the vector of fixed effects that are estimated.
Jim, would you be able to increase the font size on that window?
Yeah, totally. Yeah, thank you for reminding me. I really appreciate it. I'm kind of laughing because this is just like a real whirlwind. I mean, there's no, I don't have time. Just like all of this, it's sort of just to kind of give people a sense of how it works rather than actually give people, you know, a sufficient training that they can just, I mean, if people are following along, hopefully they are able to copy some of this, but there's also a bunch of other stuff in the output. And so these days I've got it set up where it has explicit units. And so for instance, like there's a slot called index, CTL. So the index of abundance for category 1 in 1982 is this crazy long number. I'll just divide by 1,000,000. So yeah, 1,000,000 kilograms. That's not a very useful unit, is it? I'll divide it by this. So there's about 2.4 million metric tons in 1982. That goes up to almost 7 million metric tons of pollock in the Eastern Bering Sea by 2014. So, you know, the point being that this sort of fit model object has a bunch of output that reflects what you're seeing in the plots. And so, you know, somebody who wants to make these plots again in ggplot can dig into the output and pull out what is also being summarized by plot, the plot function. So anyway, that's the half-hour chunk that we have for this. And I'd like to take a 14-minute break at this point, but if anybody has sort of a short kind of 2-minute question, I'd be happy to take it now.
I have a quick question. I think that's short. When you're setting up the data, can you have missing time? So I saw that you did yearly, but what if you wanted to do like month, year, and you had some years missing?
Yeah, so there's a bunch of kind of flavors of that. I mean, the short answer is yes. So, you know, in that wiki, there is an example of doing seasonal and interannual variation. And so, you know, there in that wiki example has links to a reference for that. where we've looked at it in detail. And then it has this kind of ugly, I mean, the way we set up the model is to have a season specific spatial term, a year specific spatial term, and then an autocorrelated space and time evolution of the distribution of the stock. And so there's a bunch of different terms kind of running around, and we have to pass those in as covariates. And so this is sort of not an example that I typically start with, but the you know, the call to fit model looks like this. It's not so much longer.
We aren't seeing your screen, if that's what you're.
Okay, yeah, I think, keep reminding me. I'm sorry to need it. Yeah, so this seasonal example, I'm sorry. Yeah, so I got to there by clicking on seasonal and annual variation, the 8th example. And, you know, I mean, this is like, I don't know, 150 lines of code. And, you know, so it's not horrible to do, but I don't think anybody's going to be able to read this immediately. You know, by the end of this chunk today, hopefully people will be able to understand parts of that, and we could just email back and forth about the details.
Perfect, thank you.
Yeah, there's another, I guess I should have said, you know, before getting way into the seasonal model, there's, you know, the other flavor is that, like, a lot of times, like, for instance, like in the Gulf of Alaska, we have a survey every 3 years for a while and then every 2 years. And so if you turn on autocorrelation across time, you can predict what the map of densities would look like even a year that you didn't sample, or you could forecast into the future. And so that, without getting into the kind of seasonal scale, you know, there's a lot of reasons to kind of care about predicting in times that you don't have sampling.